Welcome, fellow chemists, to the second video in the instrumental analysis series on infrared spectroscopy. In this video, we will focus on the variety of carbon-hydrogen bonds. Like in the video on functional groups, you'll get a chance to use your new knowledge on two practice spectra. Previously, we saw these bonds showing up as peaks around 3000. If you think about it a moment, that's quite vague as there are many types of carbon-hydrogen bonds. It turns out what is typically described as a continuous range is actually a disjointed set containing four distinct bond types. The first one is between hydrogens and sp carbons. This bond stretch requires quite a lot of energy, so it shows up furthest to the left around 3300. As the s character lowers, the stretch requires less energy, so the bond between hydrogen and sp2 carbon shows up a bit to the right. Finally, on an sp3 carbon, the peak range moves even further to the right. There is, however, one more stretch, and that is for that bond to hydrogen on an aldehyde, where there are two peaks around 2820 and 2720. Though we've seen it already, I should put the benzene ring on the screen again. After all, the ring is composed of sp2 carbons, so it is worth checking for if there was a peak in the range for hydrogen and sp2 carbons. Though the spectrum reference is helpful, I do like having this information in chart form. We have more to come, so I split this video's reference into two. The remainder of the carbon-hydrogen absorption bands are caused by bending vibrations. These require less energy, and so they show up further to the right on the spectrum. The first range is rather narrow and represents bending between hydrogen and sp3 carbon. Then if one of them is a CH3, either at the end of a parent chain or as a separate methyl group, there will be another peak around 1370. The remainder are carbon-hydrogen bonds on an alkene. A monosubstituted terminal alkene will have peaks around 990 and 910. The transalkene peak is around 970. A disubstituted terminal alkene peak is near 890. Trisubstituted alkenes have a peak between 840 and 800. And finally, the cis-alkene peak should fall within 730 and 675. As you can see, it is quite crowded in this region. Yes, I could have modified the axis to spread things out, but this gives you an idea of how tricky it will be going forward. Also, it shows the value of having the same information in an easier to read table. So now to put a real spectrum on the screen, and it's your task to try to identify what type of carbon-hydrogen bonds this hydrocarbon has. Starting from the left, this molecule doesn't contain a hydrogen bonded to sp carbons, but it does contain hydrogen bonded to sp2 carbons. There are also hydrogens on sp3 carbons, but there is no aldehyde. The strong peak between 17 and 1600 is most likely the carbon-carbon double bond mentioned in the previous video. Since we have hydrogen on sp2 carbons, this is not surprising. A benzene ring is composed of sp2 carbons, but the peak around 1600 is missing, so that is ruled out. We know there are hydrogens on sp3 carbons, so this peak is expected. Since there is another peak just to the right, it indicates there is a CH3. We now get into the complicated territory of all the various alkenes, and is not a monosubstituted, nor is it a transalkene. The peak just shy of 900 means the alkene is terminal. We then find it is not a trisubstituted or a cis-alkene. While we have determined that this molecule is a terminal alkene with some sp3 carbons and CH3 somewhere, that's pretty much all we can say. With the new hydrocarbon spectrum on the screen, demonstrate your skills again and identify the bond types. This molecule, like before, contains no hydrogen bonded to sp carbons, does have hydrogen bonded to sp2 and sp3 carbons, and has no aldehyde. When we get to the benzene, we see the unique set of peaks indicating its presence. After that, we confirm the sp3s along with the possible CH3 or separate methyl group. As for the alkenes, the molecule does not have a monosubstituted terminal alkene, transalkene, or disubstituted terminal alkene. There is a slight hint of maybe a trisubstituted alkene, but there is absolutely cis-alkenes, which, if you look at a benzene ring, makes a lot of sense. We have done a good job of identifying components of this molecule, but we do not have enough information to say for sure what it is. However, if we had more information, such as a list of potential identities, we might be able to pin it down. So feel free to give this one a go while I get started on developing the practice video where we will finally use IR spectroscopy to identify compounds. Until then, thank you very much for watching. Please leave any questions or requests in the comments below.